In this video, I want to take a look at the gradient for a function of three variables. And I should say that everything that happens with two variables is happening with three, and you could keep doing it with four variables or more, right? But here we go. Suppose I've got a function of x, y, and z, and we define the gradient of that function as gradient of f is a vector, and that vector is got three components. It's got the partial of f with respect to x in the first component, the partial of f with respect to y in the second component, and the partial of f with respect to z in the third component. And here's a bunch of things that it does for us, very similar to what the gradient of a function of two variables did. Right? That it helps us simplify some things or even understand them a little better. If you got w as a function of x, y, and z, and we've got x, y, and z as functions of t, so you have a vector function here, r of t, then there's a chain rule. You can think of w as a function of t because you plug t in, calculate x, y, and z to get r, you plug those x, y, and z in to get f, and so you could say that w is f of r of t. Then if w is a function of t, it has a derivative. And the way you calculate the derivative is by the chain rule. Right? This was the chain rule we saw. But if you write this now as a dot product, it looks like the dot product of the gradient and the derivative of r. Right? The gradient is this one, that one, and then the derivative is the dx dt, the dy dt, and the dz dt. And sure enough, this looks just like it did with two variables. Well, not just like, because there's a comma z in here, because we now have three variables instead of two. Likewise, it was related to the directional derivative. If you've got w as a function of x, y, and z, and you've got a unit vector, and you want to know what's the derivative of that function in the direction of the unit vector, well, the derivative in the direction of u of the function f is the gradient dotted with u. And we saw that that was the length of the gradient times the cosine of the angle between the gradient and the vector u, right? Which told us a couple of things, right? That is, in the direction, if u is pointed in the same direction as the gradient, then the angle here is 0 and the cosine of 0 is 1, and you get that the slope in the direction of the gradient is the length of the gradient. Also, for the same reasons as before, if the gradient is pointing this way and you look in a perpendicular direction, then you'll have theta equals pi over 2, and that dot product will be equal to 0. So again, the gradient will be perpendicular to level, not level curves now, these would be level surfaces, right? The function w is a function of x, y, and z. The graph is out in the fourth dimension. It has level surfaces in R3, and the gradient of f will be perpendicular to the level surfaces of f. Right. Here's an example. Actually, here's a bunch of examples. We're going to get them more and more complicated as we go here. First one is just f of x, y, z is x plus y plus z. When you take the gradient of this, gradient is a vector. First component is partial with respect to x, which is 1. Second component is partial with respect to y, which is 1. Third component is partial with respect to z, which is 1. This has just a constant gradient of 1, 1, 1. And the vector field looks like this. Now, vector fields in 3D become really difficult to draw because you're trying to draw them on a plane anyway. And sometimes it's really hard to see what they are. In this one, I think it's easy enough that at any point in space, you've got the vector 1, 1, 1, and then you pick the next point 1, 1, 1, and the next point 1, 1, 1, right? No matter where you are, it's the same vector pointing off in that direction. Right? It does help to be able to roll this around in space to be able to see it a little better 3D. That all those vectors are pointing off in the same direction, right? 1, 1, 1. And so the level curves or the level surfaces are all perpendicular to those things, and they should all be planes equally spaced. And sure enough, if I look at this picture, now again, it's probably easier to see live. I've got 5 level surfaces in there. The one that goes through the origin is level 0. So I think it's level 2, negative 1, 0, 1, and 2. And notice, I know it's in that direction because the gradient always points in the direction of increasing function value. So it's saying as I move this way, the function's getting bigger. So this was the lowest level. This is level -2. This is level -1. This was level 0. This was level 1. This is level 2. Of course, then there'd be level 3, 4, 5, so on. And notice that they're equally spaced because this has a nice even slope. Now, let's take a look back here at the next example. Next example, a little more complicated. F of x, y, z is x squared plus y squared plus z squared. The gradient, well, the gradient is a vector. The first component of the vector is the partial with respect to x. The second is the partial with respect to y. The third, the partial with respect to z. And in this case, we've got partial with respect to x is 2x, partial with respect to y is 2y, and the partial with respect to z is 2z. And this looks like this now. It looks like everything is pointed away from the origin. So again, easier to see in motion. Yes, everything is pointed away from the origin. The graph of this thing is like a paraboloid, but it's one dimension bigger than that, but it starts off small and gets, as it goes up, it gets bigger. I mean, the cross sections are spheres. Actually, that's that next picture. The level surfaces now, that is, take this thing and set it equal to a constant. Well, if that constant is negative, you don't get anything because this is all positive numbers. So the smallest constant you could get would be 0. That would be just the origin. And then any positive number, you'd be getting a sphere of radius, the square root of that number, right? So this picture here is showing one such level surface. So this is one level surface here that if I show you different values, so I have this slider set so that the value that's showing here, 0.44, is being plugged in for A. So this is x squared plus y squared plus z squared equals 0.44. Right? The lowest it could possibly be is 0, and then the sphere goes away. And every one of the level surfaces is a sphere. And notice that at each point on the sphere, right, pick a point on the sphere, you see that the gradient is crossing it perpendicularly because the gradient is perpendicular to level surfaces. For a function of 2 variables, it was the gradient is perpendicular to a level curve. For a function of 3 variables, it's the gradient is perpendicular to the level surface. Let's look at the next example. X squared plus y squared minus z squared, right? The level surfaces are now going to be hyperboloids, right? And this, again, is really hard to see. I get some idea of stuff going down and stuff coming up, but let's see here. So this one, again, when I think of functions of 3 variables, I think of them as temperature functions, right? So this one, what I see, the gradient, remember, is always pointing from low level to high level. So what I see is cold temperatures at the top and cold temperatures at the bottom, because everything's pointing sort of towards the xy plane. So as you move towards the xy plane, it's getting hotter, right? The temperature is going up. But then as you get to the xy plane, I see that stuff around the xy plane is shooting outwards. So cold top and bottom getting warmer as you get to the xy plane, but also then getting warmer as you move out in the xy plane. So this doesn't really help me. Well, it does help me a little bit visualize what's going on in the 4th dimension, but I can definitely see how this is getting bigger, right? That is, I got low levels top and bottom, low levels temperature, and then it gets hotter as you come towards the xy plane, but then it gets hotter as you move out to the fringes of the xy plane, right? Let's look at the the level surfaces here. I think if I just do this, I can put the level surfaces in there. Now I've got the level surfaces in there, and you can see that for negative values of A, this is the hyperboloid of 2 sheets. Doesn't seem to want to work for me here. It's a little slow. For positive values of A, it's hyperboloids of 1 sheet. At 0, it was a cone. But again, I want you to look at where the gradient crosses that surface. Every time it crosses, it does so perpendicularly, right? These are perpendicular there. Because the gradient is perpendicular to the level surface. Okay. Let's do one more example. There's that picture. This last example is x times y times z. The gradient, of course, is a vector, partial with respect to x, partial with respect to y, partial with respect to z. In this case, partial with respect to x is yz, partial with respect to y is xz, and the partial with respect to z is xy. This is a real crazy graph, which I neglected to link. Maybe this one's linked. This one has the one level surface put in there. Yes, I do have it linked. Good. So you can see all kinds of crazy stuff here. Boy, there's stuff that's pointing in towards the origin, there's stuff that's pointing out. So it looks like I've got cold temperatures over here, sort of getting hotter as I get towards the origin, but at the origin, you want to move away from it this way. That, I mean, because this would be coming in, right? The arrows are always pointing you uphill. They're pointing you towards hotter temperatures. So it looks like this actually looks kind of like a monkey saddle in 4D, or maybe an elephant saddle. I say elephant because an elephant has 4 legs and it would need 4 places to go down. And these are where you're seeing the surface right now are the low regions, right? Because the arrows are pointing towards the origin. And then these other quadrants or octants that don't have the surface in it at the moment are the high regions. Right? If I slide this thing, you can see the different, this for negative values of f, and then at 0, it's actually all the coordinate planes. And then for positive, it's those. So it switches. There's negatives getting higher and higher temperatures as we go this way. Right? Lower temperatures there, higher temperatures here. Yeah, so the gradient, whether it's a function of 2 variables or 3 variables or 4 variables, is telling you about how the function is getting bigger, or if you think graphically, how it's getting higher, right? If you think temperature, how it's getting hotter, points in the direction of most rapid increase.